So this is about semiconductors. Okay, let's learn about semiconductors. Those days they used to have something called vacuum tubes. Vacuum tubes are big glass tubes which is called the quartz window. There will be a cathode and an anode for emission of electron, collection of electron. This is how the vacuum tube is. So vacuum tubes, if you want the electrons current to flow like this, you'll keep this as negative and this as positive. If you want to change the direction of the current, you can keep this positive and this is negative. So then it allows vacuum tubes allows unidirectional current to flow through it. Unidirectional current to flow through it. You need a high voltage to operate this. You need a high power to operate this. It allows this is an advantage unidirectional current, but it needs high voltage, high power. Its longevity is not long lasting. Those days the computers used to be made up of this, the TV, Dappa TV, the big huge box TV, remember? Those were made up of vacuum tubes. So then it occupies a lot of space and it's not eco-friendly. Once kettu pochuna, you would get buried under the earth and it's not eco-friendly. So there are many disadvantages of vacuum tubes. அப்போல்லாம் பழைய டிவிலாம் பிக்சர் டியூப் போயிடுச்சு இது போயிடும் because it needs high power, high voltage, not long lasting, quite bulky, and it needs vacuum to operate. So then many are disadvantages. The scientists in late 1800s, like 1875 or so, they discovered something called semiconductor. What is this material? Is what they buried deep and buried under the earth. They found this group 14 element. Group 14 elements, such as what are group 14 elements? There is carbon, silicon, germanium. Then you have lead, tin, and tin, and then lead. These are all the group 14 elements. However, only silicon and germanium in this were classified as semiconductors. Okay, carbon is classified as an insulator. Why is carbon considered an insulator? Because it's up in the periodic table. How is the periodic table? Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Then sodium, magnesium, aluminum, silicon, phosphorus, MsPs, chlorine, and argon. Then it's potassium and calcium, and then it goes on like that, correct? So then therefore this is group 14. The group 14 has got carbon which is up in the period. This is called group. This is called group. This is called period. Okay, this is called the group. The vertical column is called the group. This 14th group, but the period wise, this is in the second period. Can you see hydrogen, helium is the first period. Second period is where you have carbon. So then therefore it's in the up in the period. So electron affinity, the size of the atom is lesser. The electron affinity is greater. So since electron affinity with the nucleus is greater, it's very hard to remove an electron. That's the reason carbon behaves like an insulator. You cannot classify it as a semiconductor. Only silicon and germanium are semiconductor. Tin is considered to be a conductor. Lead is very toxic, so they don't even use lead for anything. Okay, so then in this group 14, only silicon and germanium. This is called tetravalent. Tetravalent because it's group 14, it's got 4 electrons in the outermost shell. So that's what's classified as a semiconductor. Okay, so then now there are pure semiconductor and impure semiconductor. We learned about gallium arsenide, which is also semiconductor, which learned it in this lesson, current electricity. Remember, but that was a compound semiconductor. It's made up of, it's like an alloy of gallium and arsenide. So compound semiconductor. The simple silicon and germanium are classified as simple semiconductors. We're learning about simple semiconductors. So in that there are two forms. Pure form of semiconductor, which is called intrinsic semiconductor. Intrinsic is called the pure form. But however, there's nothing which is impure. There's 1 out of 10 to the power 10 part of impurity is still present. Like you say ideal gas, but you really don't see ideal gases, right? Like the ideal fluid, no kadayadu. It is pure, but still, because semiconductor is very, very small, even a dust particle can serve as an impurity. So anything which is pure, it will still have some impurity, which is very less. And it's pure silicon, pure tetravalent element. Take a tetravalent silicon and surround it by silicon on all the 4 sides. So you see 1, 2, 3, 4, 1 covalent bond. See 1, 2, 3, 4, 1 covalent bond. 1, 2, 3, 4, 1 covalent bond, and silicon here 1, 2, 3, 4, 1 covalent bond. So one silicon surrounded by 4 silicons, one tetravalent silicon surrounded by 4 tetravalent silicon on all the 4 sides, forming 4 covalent bonds on all the 4 sides. So like this, you have to extend the structure. You have to draw one silicon here, which has got 1, 2, 3, 4, the covalent bond. A silicon here, 1, 2, 3, 4, and then a covalent bond with this covalent bond. Continue the structure like that, 1, 2, 3, 4. Make sure that you're drawing it pretty well. Okay, this is forming a bond with this, and of course like this. Okay, so like this, you continue the structure. The structure keeps on extending. This is like a crystal. Okay, so then so what happens in this is the advantage of semiconductor is you don't need a vacuum. The semiconductor is like this crystalline structure in which the electrons will flow on the surface. And there's also something called hole. When an electron leaves, it leaves behind a hole, and the hole is flows within the core. Surface layer electron flow, other core layer holes are flowing. So therefore, you don't need a vacuum. It's a small structure, that's enough. So then, this is what a tetravalent, a pure intrinsic semiconductor is, a tetravalent silicon or a germanium. Germanium was also tetravalent, surrounded by 4 other germanium. Here we are talking only about silicon, forming 4 covalent bond on all the 4 sides, and on giving some energy which is sufficient enough to break the covalent bond. The electron breaks away from the covalent bond, leaving behind a hole. As the electron leaves, there's a hole which is created. A hole is called electron vacancy. This hole is called electron vacancy, is what is called the hole. And so then number of electrons is always equal to number of holes. This is what is about intrinsic semiconductor. It's a pure form of semiconductor. So let's talk about in extrinsic semiconductor. Extrinsic semiconductor is an impure form. An impure form, we are actually using a dopant, okay, whose size is in comparison with the host. Supposing you are taking a silicon and doping it. Okay, you can either dope a silicon with an aluminum, which is a trivalent, or with a phosphorus, which is a pentavalent. When an aluminum is doped, it's a trivalent, and it's called a p-type, and a phosphorus is getting doped with a silicon, it's called an n-type, or it's called a pentavalent element. Obviously, you know, this is aluminum is trivalent. So this is what forms a p-type intrinsic extrinsic semiconductor. The n-type extrinsic semiconductor, impure semiconductor, where we are doping. What is doping? Doping is adding an impurity. What is the impurity? It may be group 13 or group 50. If you are adding a group 13, such as aluminum, group 13 is aluminum, group 15 is phosphorus. So let's do a group 13, which is, so it's classified as a p-type semiconductor based on group 13 elements. Group 13 elements is the dopant, which is called a trivalent element, a trivalent impurity. So let's take aluminum and place it at the center. It's got 3 electrons in the outermost shell because trivalent. You are bonding it with silicon on all the 4 sides, forming one covalent bond here. 1, 2, 3, 4 forming a covalent bond. 1, 2, 3, 4 forming a covalent bond. And if you see in this, it's deficient of 1 electron. Okay, so then this is called hole, a pre-existing hole. Like this, in every structure there is a hole which is already existing. So in this, number of holes will naturally be greater than number of electrons. So you are able to change the charge carrier concentration. In this, Ne is equal to NH. This is called Ni is called the charge carrier, intrinsic charge carrier concentration. Intrinsic charge carrier concentration, which is Ni. Okay, so Ni may be E or Ni may be H. So that's what it is about. So when you write a note on a pure semiconductor, it's an intrinsic semiconductor. So you know that one tetravalent silicon is bonded by 4 other silicon on all the 4 sides, forming 4 covalent bonds on all the 4 sides on excitation such as heat energy or light energy sufficient enough to break the covalent bond. Electron is set free, leaving behind a hole. Electron vacancy is called the hole. Number of electrons is equal to number of holes. In general, Ni is referred to as intrinsic charge carrier concentration. Now, this number of charge carriers in the intrinsic charge carrier concentration is also proportional to e to the power minus Eg by 2 kT, E ionization energy by 2 kT, where T is the temperature, K is Boltzmann's constant, and Eg is the ionization energy. We'll talk about this later. So just this extra point you can write just to get more marks. That's all pure semiconductor. So in extrinsic, it's a p-type. P-type, you're doping it with aluminum, which is a trivalent element bonded by silicon on all the four sides, thereby leaving one of the covalent bond as electron deficient. And the electron deficiency is called holes. And now you can complete the structure. You can have one silicon here also. And the electron from the adjacent silicon will come and fill in this hole. Thereby the hole keeps on moving. You understand? And so hole current, and the hole keeps on moving within the core. Can you see? So that's what is number of holes is greater than number of electrons in this. And so that's all it's about. So it's also, since it's able to accept an electron, this hole is able to accept an electron. So we can call it as acceptor impurity. You should write those reasons why it's called acceptor impurity. So p-type semiconductor is where a trivalent group 13 dopant such as aluminum is surrounded by a tetravalent silicon on all the four sides, leaving one of the covalent bond electron deficient, which is called holes. So then electron from the adjacent bond of silicon comes and fills in this hole. Thereby the hole keeps on traveling in this, generally number of holes is greater than number of electrons. It's called acceptor impurity for the fact that it's able to accept an electron. Are you clear? That's about p-type. And let's talk about n-type semiconductor. Is group 15 element. Group 15 element is phosphorus, which is a pentavalent. So trivalent impurity, here it's a pentavalent impurity. It's here it's acceptor impurity, in this it's a donor impurity. That is one phosphorus, which has got 5 electrons in the outermost shell, is getting bonded with silicon on all the four sides, forming a covalent bond on all sides. Leaving one electron which is already loosely bound. You should write this word. It's a loosely bound electron which is not even a part of any other covalent bond. So very small excitation itself, the electron is able to conduct. So in this, there's already pre-existing electrons. So generally number of electrons is much greater than number of holes in this. P no solvanga, H no solvanga, holes ku eppadi vena sollalam. So then complete the structure. This is what is n-type. It's called pentavalent. It's called donor impurity because able to give an electron, donate an electron for conducting, and it belongs to group 15. The size of the dopant is always relatively compared with the host as same size as that's why we're choosing silicon and phosphorus. However, you should also know that we could also choose elements such as indium and arsenic. Okay, so indium is a trivalent and arsenic is a pentavalent, which is okay just next to this of the period. So it's okay, you can also dope it with silicon or with the germanium, whichever you want you can dope it. This can also be chosen. These are two other examples of dopants that you know. So by adding a dopant, you are able to manage, increase or decrease the charge carrier concentration. You want the holes to dominate, then you can add a dopant like that, or electrons to dominate, you can. So that's the advantage of doping. Okay, so now this is about basic difference between n-type and a p-type. You must draw the structure. Now is about band gap theory. What is a band gap theory? This is called a valence band. This is called a conduction band. Valence band is nothing but the outermost shell of the valence octet. You know, every atom has got a outermost shell. So the outermost shell of an atom, which consists of electrons, which has electrons which have the ability to conduct. But in the valence shell, valence band, it will not conduct. It has to, in order to conduct, it has to jump from valence band into the conduction band in order to conduct. So conduction band is where the electrons are conducting. Where the electrons are conducting. So the electron jump from the electron jump from valence band to conduction band in order for it to conduct. So conduction band is where the electrons can conduct or flow. Correct. In valence band they are not flowing, they are just their free electrons outermost shell. So this gap is called Eg, which is called ionization energy. It's called it's called energy gap. It's called energy gap. It's also called forbidden energy gap. Forbidden energy gap. The word forbidden refers to no electron will be there between valence band. Forbidden. In the region you're forbidden from going there, now you can't go there. The electrons are forbidden from this going inside. So in this region there will be no electron. This is called energy gap. Okay, இது வந்து ரொம்ப important for energy gap for a pure semiconductor. So if you see for an let's go to this pure semiconductor. We can add more points to it. The Eg for silicon is 1.1 electron volt, and Eg for germanium is 0.72 electron volt. This is the energy gap generally for silicon and germanium. You can also write a note on this. So then coming back here, you know that this is what is a forbidden energy gap. This much energy is required for the electron to jump from valence band into a conduction band. So what is a valence band? It's the outermost shell of the atom where the electrons are present, which has the ability to conduct. But conduction band is the band where electrons are really flowing and constituting to electric current. So they understood the basic difference between valence band and conduction band. So I'll explain to you the difference between. You have to explain the difference between metals, insulators, or semiconductors and insulators. You have to explain this difference. In general means, resistivity of a metal is low, the resistance is low, so it can conduct, whereas insulator resistivity is very very high, resistance is very very high, so it can't conduct and all that. And in semiconductors it will be somewhere between insulator and conductor, correct? Metal, correct? But that's a general difference. But they ask you to find the difference in terms of band gap theory. For a metal, this is the valence band and this will be the conduction band. And can you see it's overlapping valence band and conduction band. There's no clear energy gap, correct? And that makes every metal to be easily conducting. For an electron to jump from valence band to conduction band, it's not even difficult because already they are overlapping. So for a metal, just the free electrons have the ability to conduct, whereas for a semiconductor, if you see, this is the valence band, so conduction band is valence band. It's lesser than 3 the energy gap will be lesser than 3 electron volt. So this is the conduction band and this is the valence band. For an insulator, if you see, the gap will be much more. It's greater than 3 electron volt. It makes it very very difficult for it to conduct. So this is Eg is greater. That's the basic difference between metal insulator and metal semiconductor insulator. I'll tell you what is a Fermi level. A definition for Fermi level. Fermi level is a level where the highest energy level in which electrons are present at 0 Kelvin. At 0 Kelvin, which is absolute zero, electrons can already be present in that Fermi level. Okay, for example, in this, the Fermi level, I'll draw the Fermi level in red color. This red color line is called Fermi level. The Fermi level's position varies for a metal. It's lying in the overlapping region. Whereas in the semiconductor, lying somewhere between valence band and conduction band, and in the case of insulator also. So at 0 Kelvin, the electrons can be present. At 0 Kelvin, the electrons can be present here. And when you raise the temperature, it is just a question of the electron jumping from Fermi level to the conduction band. But we don't talk about Fermi level anywhere. We just say it and leave it like that. Okay, you understand this and leave it like that. Let's talk about using band gap theory. You have to explain a p-type intrinsic semiconductor, a pure semiconductor, intrinsic semiconductor. Let's explain the band gap theory. This is the valence band and this is the conduction band. In valence band, you have different layers. This valence band and that's conduction band. Valence band and conduction band, you have different intrinsic semiconductor is a pure form of semiconductor. You already know what is Eg. I just told you the Eg is 1.1 electron volt for silicon and 0.72 electron volt for germanium. And you know that when an electron jumps in drawing pairs, electron exists as pairs in dumbbell shape, chemistry. So you know the number of electrons will be here. Number of electrons is 2, number of holes is 2, because you want to show that Ne is equal to NH. If you're going to draw 2 more electrons in this, Then draw 2 more holes here.
Okay.
So don't leave everything in the valence band. You can't leave it empty. You have to have more electrons in valence band. Either the conduction upon electron. What is in the conduction band is what is gone to conduct. So you still can draw 1, 2, 2, 3. But still you have to compare. When you compare, you can't compare these electrons only. You have to compare only the electrons left and the holes here. So Ne is equal to NH. So this is the diagram. You've represented everything here. This is called EC, energy of the conduction band. This is called energy of the valence band. And Eg is equal to Ec minus Ev. That's all. This is about intrinsic semiconductor. Let's talk about impure extrinsic, in which we have a p-type semiconductor. This you have to draw, take it at T is greater than 0 Kelvin. You have to mention that, okay? Because T is equal to 0 Kelvin, nothing will be conducting. It will be there only in Fermi level. It won't jump to the conduction band.
Okay.
So then now it's about extrinsic p-type semiconductor. P-type semiconductor, you again draw the valence band and you draw the conduction band. In this you do various levels. Here also you do various levels. But in this, it's that it's p-type, which is an acceptor impurity. The acceptor impurity will have an acceptor energy level Ea, which will be just above the valence band. This conduction band and valence band has an additional energy level because you doped it. There's an additional energy level known as acceptor energy level, which is just above the valence band. And the advantage is now in the acceptor energy level itself, there will be electrons. So in order for it to jump to the conduction band, can you see the energy gap is reduced?
Yes.
Before it has to jump from EV to EC. Now it has to, the EG, ionization energy, is just EC minus EA. The advantage is the energy gap is now reasonably reduced, and you can understand that the energy gap for p-type is 0.05 electron volt. That much reduced. And so then when you hit p-type, holes are dominating. To show that holes are dominating, holes cannot jump. Only the electron can jump. Just draw 2 electrons here. But make sure you're drawing many holes. No.
Many.
And then a few electrons. These electrons are always there in the metal, so you can't, only the holes have to, this hole and this electron you compare, NH is much greater than Ne. Every point is in this. And again draw T is greater than 0 Kelvin, just put this, and that's about extrinsic semiconductor. So now let's talk about N-type semiconductor. You draw the valence band and you draw the conduction band, and you do the energy levels in this. And in this is N-type semiconductor, which is as a donor impurity, is able to donate an electron, correct? So you draw the ED, which is just below the conduction band. Just below the conduction band, which makes it very easy for it to conduct. A 0.01 electron volt is sufficient for it to jump. And this is what now is EV, and your ionization energy is EC minus ED. It's considerably reduced, and you know the value is 0.01 electron volt. And in this is N-type, so you should have more electrons. So just draw pairs of electron, more pairs of electron which has jumped, and draw lesser number of holes. Correct? And leave the rest with the electrons. And so this means Ne is much greater than NH. Every point is here. You have the Ag energy gap also. You have talking about donor energy level, which is present just below the conduction band. The advantage of doping is the energy gap is getting reduced. So you can also include that in general. If you want to talk about the difference between a p-type and an n-type, you know that the advantage of doping a p-type, the energy gap get reduced to 0.05 electron volt, and this energy gap is getting reduced to 0.01 electron volt. Correct? Because it creates an additional energy level known as acceptor energy level. Acceptor energy level. In this, that creates an additional level known as donor energy level, ED. This is just above the valence, just above valence band, but this is just below the conduction band. These are the extra points. Make sure you write it as proper notes, and then every point is there. And this is how we explain the band gap theory. Okay, that clarity should be there. Next is, again here also you put T is greater than 0 Kelvin everywhere, because at 0 Kelvin there will be only Fermi level, you know that, okay. So then the next thing that I have to talk about is band gap theory is over. That's all. You're very clear about all that. Now let's go to a PN junction diode, a P type and an N type. You know what is a P type? Group 13 doped. What is the N type? Group 15 doped. Combine both these together, like P and N together. It's not like a bread sandwich where you place a P type and N type. It has been good in a semiconductor factory. They grow the crystal of a P type and N type together in such a way that they have a junction. This is P type. This is N type. So then they can also represent it like this. This is P type. This is a P region, and this type is a N region. The moment this is P region and N region, P region has got more holes. Majority, correct? Minority is electrons. N region has got more electrons. The minority is holes. So how to start? First sentence that you should do, at the junction. At the junction, the charge carrier concentration is high. Charge carrier concentration is very high. What is the meaning of that concentration is high? So supposing you're standing at the signal, so cars will be so close to each other, the bikes will be so close. As you go away from signal, there will be little distance. So at the junction, the carrier concentration is always very, very high. So then at the junction, charge carrier concentration is very, very high. So the first point. Due to this, what happens? Holes from N type move to holes from majority. Holes from P type move to N type, and the electrons from N type move to P type, which is called majority charge carrier. Flow of majority. Flow of majority is called diffusion current. It's called diffusion current. Okay, as more and more diffusion current flows through, it leaves behind, as holes leave the N type, leave behind immobile negative ions at the junction. As electron leave the N type, it leaves the immobile positive ion at the junction.
Okay.
Which creates an electric field in positive to negative, emanating from positive, terminating in the opposite direction. Initial electric field is first from P type to N type. Now what's happened? It's created an additional electric field which is from N type to P type. N-type. So there is as more diffusion current flows, it leaves behind immobile ions. The word immobile ions, where negative ion in P type and positive ion in N type at the junction, which creates an electric field which is from N type to P type. More is the diffusion current, and more is the charges deposited, and this electric field region widens. It's called depletion region. The electric field region is called depletion region, which is deplete of charges. Adla charges obviously it will emanate from positive and terminate in negative. This depletion region widens, and this creates a potential barrier VB. It creates a potential barrier VB, which reduces the diffusion current, which increases the flow of minority. This potential or electric field causing minority to flow. Causing minority. What is minority? That is electrons from P type move to N type, and holes from N type move to P type. It's called drift current.
Okay.
It's called drift current. This also reduces. So you should write diffusion current decreases. Drift current increases. At some point, diffusion current becomes equal to drift current. It's called equilibrium. So when you buy a PN junction diode, it will be in equilibrium. You won't feel any flow of current. So this is the state. And when you connect it to the circuit, you disturb the equilibrium. Let's see how to disturb the equilibrium. Take a PN junction diode and forward bias it. A P type is connected to positive, N type is connected to negative. It's going to disturb the equilibrium. Let's see how it is. The applied voltage is in this direction. You know that the barrier potential is from negative to positive. They both are in opposite direction. So the applied voltage slowly overcomes the barrier potential and starts applied potential slowly overcomes the barrier potential VB. Okay. So then it's V minus VB is the net potential. Net barrier potential decreases. Can you see? The barrier potential decreasing. Barrier potential decreases, diffusion current increases. Diffusion current increases. Flow of majority carriers. Majority carriers starts flowing. Thereby allowing the ammeters show deflection. Are you clear? It will show milliamps deflection. Milliamp current will flow through. So what is it? We're going to disturb the equilibrium. That means you're going to forward bias it, which means P type is current to positive terminal, N type is current to negative terminal. The applied voltage keeps on increasing. The barrier voltage is still from N type to P type. Slowly, since they are in opposite direction, net potential decreases, the barrier voltage decreases, and diffusion current increases. The majority starts flowing and constituting to milliampere of current. So what is happening in forward bias? Let's talk about reverse bias. Take a P type and N type, connect the P type to negative terminal, connect the N type to a positive terminal. It's called reverse bias. In reverse bias, you see that the barrier potential is still from negative to positive, but applied potential is also in the same direction, which gets added, and so the barrier potential actually increases. The potential in the junction actually increases. So only drift current will flow. Only drift current can flow. The diffusion current cannot flow. Drift current is minority. Minority means it's microamps current. A microamps current is as good as no current. Reverse bias mode is always treated as non-conducting, though it conducts a minority. Correct? So then let's draw a graph for this. In the forward, this is forward bias, positive voltage, this is negative voltage. This is milliamps current, this is microamps current. You must ensure that the graph is touching the x-axis for some increase in voltage, applied voltage. I told you, as you keep on increasing, it has to overcome the barrier voltage when the current starts steeply rising. And this is called the knee voltage or threshold voltage. Threshold voltage at which the applied voltage is able to overcome the barrier voltage and it starts to conduct. The reverse bias mode is microamps current. So current here this is called breakdown voltage. V breakdown. We don't talk much about it, okay, because this is almost like a non-conducting mode. You understand? It's a reverse bias current, which is microamps. We consider it as non-conducting mode anyway. So this is what it is. This is the graph, very, very important. The knee voltage for silicon is 0.7 volts, not electron volt, it's volts. And for germanium, it's 3 volts or something like that. So then, and therefore, that's what it is. You just understand this graph. It's forward bias. This is forward bias mode, and this is reverse bias mode. What happens? A combined diagram for this. In addition to this, for forward bias and reverse bias, you should also do this. Draw like this, okay, and draw a graph which is like this. For reverse bias, and do this and write it as VB plus V, or V plus VB. Okay, write it as V plus VB, which is higher potential. And again, another graph for forward bias mode. Make it shorter, that's all.
Okay.
This is VB, V minus VB. The barrier potential is decreased, but here it is increasing. Just to show that some graph like this, which has to go like this. Okay, next thing that I want to tell you is forward bias. And this is the right note on forward and reverse bias, or how do you disturb the equilibrium, how do you allow the current to flow through. The graph for current versus voltage. And this is showing how the potential barrier is decreasing and increasing. And then that's about writing a note on PN junction diode and forward biasing and reverse biasing. Now the next one will be about doing a rectifier. A rectifier is a device used to convert an AC into a DC. Alternating current into a direct current. Okay, so then you take an alternative current and pass it on to a diode. It will convert into DC. How to do that? Okay, there are two types of rectifier. One is a half wave rectifier. Another is a full wave rectifier. Okay, let's do a half wave rectifier first. Okay, it consists of, I would draw a transformer which is a step up transformer, but it can also be a normal transformer with equal number of turns. But the whole purpose, what is the purpose of a transformer, is to convert the voltage. The voltage is less, you can step it up before transmission, because high voltage transmission is what is good, high current transmission is not good. So yeah, high voltage transmission, MUF cell high voltage தான் 44,000 volts transfer ஆகும். Okay, நமக்கு 230 தான் தேவை வீட்டில். So high voltage transmission power consumption is Power wastage is less.
Less.
Did you learn the lesson alternating current?
Yes.
In that it will be there if you remember. So you have a step up transformer to which you are connecting a diode D, and to this you have a load resistor, RL, which is X and Y is connected. Okay, so this is connected to an input signal. The AC input is the voltage input. So this part is called a step up transformer. How do you want to step up or you don't want to step up, it's up to you, but this is what is generally I do. And where RL is known as load resistor. So what happens during the nodes, you have to write it. Okay, the input of an AC signal is given to the primary winding of the transformer. It's called the primary winding of the transformer. To the secondary, a diode D is connected in series and then in turn connected to a load resistor where the output is going to be received.
Okay.
So during the first half cycle, what happens during the first half cycle? The diode D is getting a positive voltage. Let's consider this point is P and this point is Q. The point P is getting a positive voltage.
Okay.
So diode D is getting forward biased, forward biased. So diode D is getting diffusion current, majority will flow.
Diffusion.
So the current thereby flows from X to Y through the load resistor.
Okay.
During the second half cycle, what happens during the second half cycle? P is getting negative voltage.
Okay.
And diode D is getting reverse biased, which means no current will flow from X to Y.
Okay.
So then this process continues, and so then the input voltage is like this. The output voltage is going to be diode D is conducting, then it's not conducting. Diode D is conducting, then it's not conducting. Diode D is conducting. During first half it conducts, during second half it doesn't conduct. So then this is half rectified. Can you see? The output voltage is half rectified. Correct? And so they say the frequency of the input voltage is 50 Hertz. 50 Hertz is the moment about the mean position. This is one moment about the mean position. This is also one moment about the mean position for one time period. Can you see?
Okay.
So the frequency remains the same for a half wave rectifier. So let's talk about now full wave rectifier. In a full wave rectifier, what is that you have? You have the same way you have a step up transformer, and to which you have a diode D1, and you also have a diode D2, and which is in turn connected to a load resistor RL like this. This is the point X and this is the point Y, which is in turn connected to a center tap, and this is the diagram. Okay, so then you have an input voltage which is VI, which is connected here, and the input signal comes in here. So you have to write this. Let's consider this to be point P and this point Q, and this is the center tap T, and this is the transformer. Okay, how do you write? You connect the AC input is given to the primary of the transformer, the secondary windings of the secondary. You have diode D1 and D2 which are connected to one end of the transformer coil is D1, other end is connected to D2, which are in turn connected to load resistor, and then eventually with the center tap. So let's write during the first half cycle. Again, during first half cycle, the point P is positive, whereas point Q is negative. So diode D1 is forward bias, diode D2 is reverse bias. So diode D1 conducts, diode D2 does not conduct. So during the second half cycle, the first half, during second half cycle, P is negative, Q is positive. Diode D1 is reverse bias, whereas D2 is forward bias, and now diode D2 is conducting. So eventually one of it is conducting for every half. So this is going to be the input voltage. The output voltage is D1 is conducting or D2 is conducting, or D1 is conducting or D2 is conducting. Can you see? So either way it's fully rectified output. Can you see? It's a completely fully rectified output. So this is the V input and V output, full wave rectifier. It's fully rectified. But notice this, that in this they ask you the frequency is 50 Hertz. The frequency of the output will be 100 Hertz. Why? Because it's got two oscillations in one particular time period, 0 to T. Can you see?
Yes.
So the frequency gets doubled now. And then what else you can say is this, see, if you see this is a DC, because the current always flows from the direction of the current. When P is positive, the conduction of current happens from P, X, Y, T. And when diode D2 is conducting, it will be Q, X, Y, T. Either way the current flows from X to Why? So it's eventually a unidirectional current. So it's only DC current. But however, it's pulsating DC. Pulsating DC output, correct? A DC means steady. Is it steady?
No.
So in order to convert a pulsating DC into a steady DC, you have to pass it into a filter circuit. A filter circuit which consists of a capacitor and also a resistor, which is like this. This is called a filter circuit. The filter circuit converts a pulsating DC into a steady DC. The pulsating DC into a steady DC. This is how the filter circuit does. And then is about doing the numerical part of it. Okay, so then so here are some numericals. You know that the intrinsic charge carrier concentration. Okay, before which I want to teach you one more thing is about rate of recombination, which I missed teaching. Okay, so always you know that at equilibrium, if there is at the junction, if an electron and hole is created, they both will combine.
Okay.
That's called rate of recombination. The rate of recombination at equilibrium, it should always recombine and destroy itself, because no current should conduct.
Okay.
So at equilibrium, the junction rate of the number of electrons and holes created should recombine, and the rate of recombination is always proportional to the Ne into NH.
Okay.
Number of electrons created, hole created. So rate of recombination is equal to R into Ne into NH, where R is called recombination constant.
Okay.
Recombination constant. Whereas the rate of recombination is proportional to Ni square for intrinsic. For pure, because Ne is equal to NH there. In intrinsic, Ne is equal to NH. So Ne into NH will become Ni square. So rate in the intrinsic is equal to R into Ni square. This is equation 1, this is equation 2, this is for extrinsic, this is for intrinsic. So equate both. R and R get cancelled. Ni square is equal to Ne into NH. So new formula that you get at equilibrium. Okay. So at equilibrium, you are equating both extrinsic and intrinsic, because both of them will not conduct at equilibrium. Now whether you buy an intrinsic or extrinsic. So then let's go to this kind of numericals in which the energy gap of silicon, Eg, is given.
Okay.
Calculate the ratio of conductivity at conductivity itself means number of charge carrier concentration. N is proportional to e to the power minus Eg by 2 kT, which shows that when the temperature changes, number of charge carrier concentration is also getting affected.
Okay.
So then K is Boltzmann's constant. You don't need this, but it's only extra. Okay. So then that's the first question they're asking. They will not ask you this in boards. It's only for your understanding. But what is the meaning of conductivity? It means number of charge carriers here. And what is dT is the temperature. What is Eg, ionization energy. What is K, Boltzmann's constant. So to understand this, they are giving that at 300 Kelvin, you will have one number of charge carrier. At 500 Kelvin, you will have another number of charge carrier concentration. What's the ratio of these two?
Okay.
You know the number of charge carrier concentration formula, just substitute and change the temperature as 500 and 300.
Okay.
And let's see what I have done. So you know that this is N1 and this is N2 at a temperature of 500 at a temperature of 300. The K and K, the constants gets cancelled. You can take it like an exponent up.
Okay.
It will become subtraction, e to the power subtraction. You can take the constant out and subtract and plug in the values. You get e to the power 8 to be the answer. This is again only for your knowledge. Okay. I don't think it will come. Next question, this is the second question, where the band gap again for germanium is 0.72 electron volt, Eg.
Okay.
Forbidden energy gap. Find the temperature at which the number of conduction of electron becomes double than 300 Kelvin n electrons, n is the charge carrier, when it will become 2n. At what temperature? At what temperature will it become 2n? So let's take the second question. Let's take n and 2n. You write this equation is equal to some proportionality constant proportionality. You divide both. So 1 is to 2. I'm dividing 2 by 1. Can you see? I've divided 2 by 1. So I get 2 is equal to exponents use panni mele kondu poi unknown temperature. 1 is a known temperature. You can juggle around because you know all these values. But you don't know this is E's format. Okay. And so you can leave it like that, or you can apply log on both sides. And ln 2, this is ln 2, natural logarithm. You can't do this sum because you don't know ln 2's value is 0.69. This is only for entrance, not for your board exam, just to understand how it's proceeded. So let's go to next question, just for you to understand the logic. Nothing more. Third question is about the resistivity of at 300 Kelvin is given. Do you know for a semiconductor is inversely proportional to temperature?
No, yes.
For a metal, it's directly temperature increases, resistivity increases. For a semiconductor, temperature increases, resistivity decreases, and it's a reciprocal function. So you know that resistivity is inversely proportional to temperature T1, rho 1, rho 2 is inversely proportional to T2. They've given a temperature and they've given resistivity. They've given a temperature, you have to find the resistivity, second resistivity. You know, rho 2 is equal to, so is equal to K into, correct? Divide 1 by 2, you can find. That's what I've done. Then similarly, number of charge carrier concentration, it becomes 3 times. Initially, at 300 Kelvin, it is N. Now it's become 3N. So look at the way I've proceeded this some third question. So at 300 Kelvin, it's 1 by N. Resistivity and conductivity are also inversely proportional, and resistivity and temperature are inversely proportional. So the inversely proportional is just to plug in this value and get this. Okay. So next question is the fourth question. This is where it's going to get very important. They have given in this question that it's being a donor impurity, which means the pentavalent impurity is getting added. This is the concentration. The intrinsic charge carrier concentration is given.
Okay.
They are asking for number of holes at 300 Kelvin. They have given Nd, which means a dopant concentration. That itself is Ne. Because the dopant will give you number of electrons. So Nd can be taken as Ne. So you know Ne, you know Ni. You can calculate NH using directly this formula. So then silicon diode is forward biased and a current of 10 milliamps passes through it. If the barrier potential is 0.7 volts, okay, applied voltage is 1. Whenever you have applied voltage, barrier voltage, you have to subtract that to get the net barrier potential. Okay. Subtract it and divide it by resistance to get the current. To get the resistance, you divide it by I. Okay, can I go to next one? An ideal diode. You should understand that an ideal diode is one which behaves like a conducting wire. Conducting wire in the forward bias mode. And like switch off in a reverse bias mode. Reverse bias panta, the current flow, it will behave like a switch off. Forward bias will behave like a conductor, ideal diode. Because ideal diode has got zero resistance, which means it can allow infinite current to pass through. So it behaves like a conductor. So look at this question. A DC source of 5 volt is connected in series to a resistor and an ideal diode. Determine the diode state and the current. Ideal diode behaves like a conducting wire in switch on and switch off in the reverse bias mode. So what are they asking? I am assuming the diode is switch on, which means it's forward bias. I is equal to V by this is like a wire. So you can ignore this. I is equal to V by R, you get the current. If you switch off, which means it's reverse bias mode. Can you see it's reverse bias? Can you see from the diagram?
Yes.
Yeah, positive is connected to N-type. You should identify this is forward bias, this is reverse bias. In this it will behave like a switch which is switched off, so current will be 0. They have given this sign half-wave rectifier where V is equal to V0 sin omega t. The format, V0 therefore is 10 root 2. If they ask you for a peak voltage, it's 10 root 2. If they ask you for peak current, I0 is equal to 10 root 2 by R. V0 by R. Just get this. Then they are asking for average load voltage. An average load voltage means DC. We should know the meaning. Remember we calculated I average in alternating current. AC lesson, which was due to flow of charges. I RMS was due to flow of heat. And I average was due to flow of charges. So that is DC value for half the time period. So DC means I average. So for calculating VDC, they ask you VDC, it's nothing but V average, which is for a half wave rectifier. For a full wave rectifier, we studied 2 by pi of V0. And the lesson 0.7 V0 the derivation. So either half wave not divided by 2, so it's V0 by pi. For a full wave, it's 2 by pi of V0. So next is this sum is very important sum. Silicon is getting doped by indium as well as Indium as well as arsenic. Indium is a trivalent, arsenic is a pentavalent. You're adding both. So it's like you're adding some holes and you're adding some electrons. Some electrons and holes will recombine.
Okay.
You'll be so, but there'll be surplus electrons because which is dominant is arsenic. Arsenic is a pentavalent. So subtract the number net, find the number of electrons. This will be your Ne.
Okay.
The net electron concentration will be Ne, and you know Ni square is equal to Ne into NH. Ni square is given, which is the intrinsic charge carrier concentration. Where is it given? Here. Just substitute whole square and find NH. That's all. So whenever you understand when two things are doped together, the net you have to calculate, see which is dominating. N-type is dominating or P-type is dominating. This I've already taught you how to find the frequencies of half wave and full wave. That's all. Become so thorough with this lesson.
Okay.